Hello, my name is Yachong. I'm going to do a presentation in the subject of Zeno's paradoxes and the real-world implications of limits. First of all, what is Zeno's paradoxes? Zeno's paradoxes are a series of philosophical arguments presented by the ancient Greek philosopher Zeno of Elea. The paradoxes famously challenge the notion of plurality, motion, space, and time by suggesting they lead to logical contradictions. Zeno's argument against motion contrasts the actual phenomena of happenings and experience with the way that they are described and perceived. The exact wording of these arguments has been lost, but descriptions of them survive through Aristotle in his Physics. Aristotle identified four paradoxes of motion as the most important: the dichotomy, Achilles and the tortoise, the flying arrow, and the moving rose. Let me give you a brief introduction to the dichotomy paradox. Imagine a man walking from point A to point B, 1 mile apart. Zeno argues that before reaching point B, he must first reach the halfway point, covering half a mile. To go further, he must reach the halfway point of that segment, covering a quarter mile. This process continues infinitely, with the man covering smaller and smaller distance. Zeno's paradox suggests that because there are infinite halfway points, the man would need infinite steps to reach point B. However, if we add these infinite divisions, 1/2 plus 1/4 plus 1/8, and so on, the total adds up to exactly 1 mile, a finite value. Now, let's transition from Zeno's paradox to its mathematical solution. Suppose the man takes only 10 steps. The total distance covered is approximately 0.999, very close to 1, but slightly less due to truncation. Adding more terms will make the sum even closer to 1 without exceeding it. To analyze the case of infinite steps, we use the formula for a geometric series. The total distance covered is. This infinite series converges to 1, resolving Zeno's paradox by showing that infinitely small steps can sum to a finite distance, connecting Zeno's challenge with the concept of limits. Building on the fundamental concept of limits, we now introduce the formal limit laws. These laws provide a structured method for evaluating limits of various mathematical expressions. We can perform operations like addition, subtraction, multiplication, and division on these limits. For example, let's evaluate the limit of this function. We begin by applying the quotient law 7, ensuring that the denominator is not equal to 0. Next, we use the sum law 3 and constant multiple law 5 to simplify the expression. Then we apply the power law 8. Finally, we apply the law 1 and simplify the result. Zeno's paradoxes, especially the dichotomy paradox, still influence modern science and technology through the concept of limits. In GPS systems, small updates reduce position errors, and practical limits ensure enough accuracy after a certain number of steps. The quantum Zeno effect shows how frequent measurements freeze the change in a quantum system, stabilizing qubits by preventing unwanted state changes. In machine learning, Zeno's paradox is similar to step-by-step algorithm like gradient descent. As the algorithm nears the best solution, updates get smaller, but practical limits ensure it reaches the solution in finite time. Zeno's paradoxes remain relevant in explaining key concepts in modern technology. Here are some final references. Thank you for your attention.